Hi, I'm David. Today I'm going to talk about expansion of high-dimensional cubical complex with application to quantum locally testable codes. Yeah, so so we'll construct these quantum locally testable codes with almost optimal parameters. This work is done with Irit and Toma. Okay, yep. Okay, so let's quickly review the definition of quantum codes. So a quantum code is specified by two parity check matrices, and they compose to zero. Yeah, so that's the usual definition for CSS codes. Um, but we'll often use another way to express them, which is we have three vector spaces and two linear maps, as shown here, and then they compose to zero. So the structure is also known as chain complex. And later on, if you see these linear maps, then they always compose to zero. And later on, we care about five code parameters. So N, K, D, W, and S. So NKD are pretty straightforward. They're the number of qubits, the number of physical qubits, the number of logical qubits, and then the number of polyflips that's needed to chain from one coder to the other. So that's the distance. And W here is the maximum number of non-zero entries in each row and column of your parity check matrices. So in other words, if your W is small, then HX and ZZ, they're like sparse matrices. And in particular, when we say LWPC codes, that means W is a constant. So that explains the first four parameters. We'll now talk about the last parameter, S. And this is related to local testability. Okay, and so to motivate the definition, we ask, okay, so given a bit string, how do we know if it's a code word? So one way is to multiply by the parity check matrix, and by definition, the result is zero if and only if C is a code word. Alternatively, you might say, okay, maybe it's enough to just pick a random check. And well, if it's a code word, then we know that they multiply by zero, then multiply into zero. So yeah, so maybe that's enough. And in fact, this method is particularly nice if your parity matrix is sparse. So if your parity matrix is sparse, that means this check only involves a few number. This check only like measures a few number of bits. So in this case, this check only to compute this check, all you need to know is the value of Ci, Ck, and Ck. So yeah, so this is also called a local test, meaning that you only need to know a few entries of C. Well, and the condition for being a locally testable code is exactly saying that this local test, the second method, is almost as good as the global test, which is the first method. And so in particular, we want an inequality of the following form, which is the probability of failing the test. That probability should bound the distance to the code word. And this ratio is known as the soundness, which is the fifth parameter. And more formally, you can write it in this form. So that's the mathematical expression. Yeah. And for quantum code, since there are two parity check matrices, the soundness of a quantum locally testable code would be the minimum of the two, like the two soundness parameter for individual parity check matrix. Okay, and so now we understand all these five parameters, and here's the main results. So assume the existence of some robust codes, then there exists a quantum locally testable codes with these parameters, which are all optimal up to polylogs. So you might worry about this condition, and in fact, there's a paper in preparation by Kalachev and Panteleev that showed such existence, and so together this would give you an unconditional construction of almost good quantum locally testable codes. And in some contexts, you probably really want your soundness to be constant. In that case, you can do like variants of parallel repetition, and you'll be able to get constant soundness at the expense of a larger weight or locality, also known as locality. Okay, so that's pretty cool. But you might wonder, okay, why should we care about quantum locally testable codes? And the reason is that it has a very close connection to another important open question known as quantum PCP. And so for simplicity, let me first talk about the classical version. So a PCP theorem says that there is an efficient algorithm that converts any proof into a probabilistically checkable proof. So what do I mean by probabilistic checkable proof? When you usually read a proof, you have to check every line of the proof and then make sure that they're correct. Yeah, so if there's one line that's wrong, then the whole proof falls apart. So in contrast, for a probabilistically checkable proof, all you need to do is to check, like, let's say, check 10 lines somewhat randomly. Then if they're all correct, then you have like a 90% confidence that the whole proof is correct. And you can sort of see a similarity between this probabilistic checkable proof and the locally testable codes I just explained. So where you also have some kind of, like, you just randomly pick some of the checks and then just check them. Yeah. And the connection, yeah, and indeed, like for many PCP construction, they rely on these locally testable codes. And yeah, and for the problem for quantum PCP, yeah, there's a similar variance for the quantum case. And then it seems like very likely to resolve these quantum PCP, it's quite helpful to understand these quantum locally testable codes. So that's one of the main motivation for someone to care about these quantum locally testable codes. Okay, so now let's talk about like some history, like what's known about these constructions. So here's some previous work, and here we can see that the main difference is the distance. So for these PCB constructions, you might want to have these distance be like nearly linear, and previous construction is only square root. And in our case, it's really like very close to being a linear, and that's the key improvements in this work. Of course, we also improved the rate, but I would say distance is more important in several contexts. So what leads to this improvement is actually some of the recent breakthroughs on quantum locally LDPC codes. So let me sort of describe some of these works. So here we see, yeah, so to understand these quantum locally testable codes, it's useful to know some of these simplings. So here are some other codes that are all closely related to this question of quantum locally testable codes. And in fact, the simplest version is the pretty well-known Tanner codes. So a classical Tanner, like the classical Tanner code, is a sort of like expander codes that builds on these bits and checks. So you have a linear map between your bits and checks. As we described for quantum code, now you have these x check and z check, and they compose to zero. What's interesting is that recently these classical locally testable code constructions, they also have this extra linear map. And this extra linear map characterizes the relation between checks. Okay, so it has the traditional bit to check map, but now we have an additional map from checks to the relation between checks. Right, and so for our quantum locally testable code construction, you can think of it as a sort of a combination of these tricks. So now we not only have qubits and checks, but also have relations between checks. And so together they form like 4 linear maps. And yeah, that's what our construction is based on. So, right, and so here are some, some corresponding works. So here's the Tanner code, and then here's some recent work on quantum LDPC codes and classical LTC codes. Yeah, and so what we can think is that our work is really like extending these techniques in previous works to arbitrary long chain complexes. And for our proof technique, we draw some inspirations from from this paper, DHLV, which draw inspiration from this earlier paper, DLM. Yeah, so if you look at our proof technique, there's if you trace down the details, you can see some similarity between all of them. Okay, so let's now talk about the construction. So, right, so for our construction, we start with the cubical complex. For our actual construction, we use complexes of dimension 4, but for illustration purpose, we'll mainly focus on dimension 3 because it's easier to visualize. Okay, so the input would be an abelian group and T sets of generators. So here is a picture. The vertices, there are 8 copies of G, and these form the vertices. So each vertex is labeled by an element in G and also like which copy it's in. Okay, and then the edges are formed by G and A1G, these horizontal edges, and where A1 is an element inside this capital A1. Okay, and then G is also connected to A2G and then also A3G. And since the generator has size delta, so each of these G is connected to delta many horizontal edges. Okay, so what's nice is that because this group is abelian, we have the fact that A1, A2G is equals to A2, A1G. And that means these structure would form these squares. And of course, furthermore, they would form cubes and so on. So together that forms a cubical complex. So with this cubical complex, we can now build like a chain complex. So again, chain complex is a bunch of vector spaces and linear maps that compose to zero. So and this chain complex is formed by mapping the vertices to edges and then to squares and then to cubes. More specifically, these vector spaces, they're generated by these geometric objects. So for example, this one, it's F2 to X0. And then where X0 are all the vertex set. And the next vector space is F2 to X1 and so on. And the linear maps, they're determined by the incident structure. So for example, if a vertex is in an edge, then the corresponding entry in the matrix would be 1, and otherwise it's 0. So what's nice about this is that this construction automatically composed to 0. These linear maps automatically compose to 0. And it's because for each vertex and each cube, if the vertex on the cube, square, the vertex on the square, then they share exactly 2 edges. So as you can see here. So that's why when you map it twice, it will always be 0. Okay, so that's great. So if you start from cubical complex, you can construct a chain complex. And as you say, chain complex directly give you a quantum code. So it seems like you have a quantum code, except that if you look at the code dimension is often like 0 or something that's pretty small. And so to in fact get a non-trivial code, you will need to apply the Tanner code, which means that we have to apply these local coefficients. And that's exactly our construction. And this kind of method is also known as the sheaf complex. So what we now have is that on top of the cubical complex, we also have these T linear maps. So H1 to HT. Okay, and previously the vector space is F2 to X0. Yeah, previously previously the vector space F2 to X0, which means that each vertex we assign a value of F2. But now instead we assign a value which is like a tensor. So for each vertex, we assign a value in F2 to the M1 times M2 times M3. So now overall, this vector space would become F2 to the M1 times M2 times M3 together to the power of X0. Okay, and for edges and squares and so on, we will also assign some like more extended like they take value inside matrices or vectors. Okay, so that's a vector space about linear maps. Well, what we'll do is to construct this linear map, we'll first apply this H1 transpose tensors I2 and I3. So after applying such map, we have F2 to the delta times N2 times N3. And now recall that each vertex is connected to delta many horizontal edges. So what we'll do is to split this tensor into delta layers. So each layer, and these delta layers would be sent to these delta edges. And so each edge would get a value inside F2 to the power of M2 times M3, which is exactly what's needed to construct the map. Okay, so that means it depends on which edge you would take that particular slice. So for example, this edge uses the A1 generator, then it would get the A1th coordinates among these delta layers. Okay, and then we can repeat the same thing for other maps. So for this vertical line, these edges are labeled by A2, and they would take the layer from this other map. Okay, and so on. And again, one can check that this construction gives you a chain complex. Okay, and so here's the example in 3-dimension. You can do again the same thing in 4-dimension. Then overall, you'll get 4 linear maps, and that's exactly our construction of this quantum locally testable code. Okay, so that's the construction. Let me briefly overview the proof. So the proof, the main part is proving this distance and soundness. And we have two parity check matrices. So for the first parity check matrix, HZ, the way you prove is to use the spectral expansion property of your underlying graph, and together with the robust property of your local codes. So that's one of the assumptions. That's where the assumptions come from. So we need both of these properties to show this parity check matrix has a large distance and soundness. And this follows, this uses some random walk argument, and in some sense, it's somewhat similar to these earlier like expander codes, like the earliest like Tanner code proofs. It uses these random walks. Okay, so for Hx, now the structure is a bit different. So in the forward direction, it's mapping from the 0 cell to the 1 cell to 2 cell, etc. But now in the opposite direction, it becomes 4 cell to 3 cell to 2 cell. So it's a bit different, and we need a different proof. But interestingly, for these sheaf complex, they has a form of Poincare duality. So that means you can reduce the homology to cohomology. And so in fact, once we've done the reduction, it's just the first case. So that's how the proof goes. Okay, and so let me conclude. So in this work, we show that we can combine a 4-dimensional cubical complex with the 4-dimensional robust tensor code, and together they would form an almost good quantum locally testable code. For the future direction, a natural question is, can we remove the polylog in the current construction? One possibility is that we can take a more general cubical complex from these non-abelian groups. However, this choice would impose some extra symmetry constraint on your local code. So, for example, this is satisfied by some Reed-Solomon code. But they do not have enough robustness, so to make our current argument work. So that's one of the challenge. But instead, one can choose some other complex, such as the cosine complex. But again, the local codes over there is also the Reed-Solomon code, and again, it doesn't have enough robustness for for our argument to go through. Yeah, so that's the first question. The second question is, can we make a closer connection to quantum PCP? So for example, an important question is whether we can implement transversal non-Clifford gates on these codes. And this has been recently explored in these papers. And interestingly, the local code required to support these transversal gates is again these Reed-Solomon code. And so it seems like understanding the robustness of these Reed-Solomon code or Reed-Muller codes is like, it's really like the important bottleneck, and then it's the key to resolve both of these questions. Okay, and thank you.